everybody. Welcome to our next video in Unit 11, which is all about Graham's Law of Effusion. So this video is going to be pretty short only because there's just one equation that I want to talk about. And I used to talk about this in Chem 2, and then I took it out, and then since I started teaching AP, I decided to reintroduce it, only because I think it helps qualitatively to see how gases effuse or diffuse into either a pinhole or into one another. So, and normally you won't have to use the equation to do this, but I just wanted to introduce it because I do think it is a good skill for you to know how to do. And it's much easier to learn how to do things in high school than it is when you go on to college, where I know you'll have to use this equation. So Graham's law of effusion, what is it? It states that at a given temperature and pressure, the rate that a gas moves through a pinhole is inversely proportional to the square root of its molar mass. So this is the first time we're actually introducing a square root into any sort of chemistry equation. And this definition is kind of weird, like it doesn't really tell us much, right? All you need to know about Graham's law of effusion is that gases with a lower molar mass move much faster than those with a much higher molar mass. And that makes sense. The gases that are lighter are able to move much more readily through a space. Gases that are heavy tend to stay in one spot. They're not going to move as fast. You know my favorite reference, 600-pound life. If you had me in Chem 1, I always talk about that with significant figures. But those people tend not to move very much because they're so heavy that are on the shell. And the same goes for gases. The heavier the gas, the more they don't move. They move much slower when we're comparing them at the same temperature and pressure. Of course, if we have two gases at different pressures and temperatures, we can't use this equation, but that's something totally different. Your equation looks like this, and it's interesting because it's not one we've ever seen before. So the rate of effusion of gas A over the rate of effusion of gas B, so we're kind of making a proportion here with those rates, how fast they're moving, is equal to the square root of the molar mass of B. So notice how gas B is on the top on this side of your expression here. So the rate of effusion of B is in the denominator on the left-hand side of the equation, whereas on the right-hand side, the molar mass of B is on top. Let's just go ahead and highlight this here quick. So the rate of effusion of A is equal to the molar mass of A on the opposite side. So I guess I can't change the highlighter color to show B, but you get the general idea. So let's talk about what effusion is, because effusion is something very, very specific, and it kind of states it here in this definition. Effusion is when a gas leaks through a pinhole. So if I look at these two images right here, this right here is effusion. So you have this little pinhole that's in between these two chambers. So let's go back to just the pointer here, the arrow. I have this gas in one side of the chamber. I have helium gas. And then I have this pinhole that's separating those two. And this was previously empty. That's why it says evacuated chamber. This helium gas is going to move through this pinhole at a certain rate. In another system, however, I have ethylene oxide. So ethylene oxide has a significantly higher molar mass. You'll see here's the formula down here. And when I have this same exact volume, so notice the volume is exactly the same, the pressure is exactly the same. We have the same number of particles in each one of these systems. The temperature is also the same. So that's important here. So let's write this down. So these are at the same pressure, so I'll put same P, and they're also at the same temperature. That's important. Nothing is different between these two systems. Because ethylene oxide is much heavier, it has a higher molar mass, this effuses much more slowly, and that's because it can't move as fast. It's too heavy to move very, very fast. You can even think about it in terms of rocks on a stream. right? I take my daughter to the creek a lot because she loves just throwing rocks in the water. But the heavier rocks are not going to move nearly as fast because they're too heavy. The smaller rocks are much easier to either move with the water or to throw. So this one is going to effuse much more slowly than this helium because, again, it's much heavier. So that's just a qualitative description of Graham's law of effusion, and it's pretty simple. It makes sense. What we can do, however, is use this equation to quantitatively determine rates to their molar masses. So let's go ahead and do that together in this next sample problem. So let's keep this equation on the screen up here and do sample problem 13. We're going to do all of these together because they are a little bit different from one another. So like I was explaining in the PowerPoint section of this, gases that are much lighter, that have a much lower molar mass, can effuse much faster than ones that are heavier. Effusion is how fast a gas can move through a pinhole, like I was mentioning in the other video. So actually, let's take this image because I wanted to mathematically relate each of those gases to one another using Graham's law of effusion. So that's what sample problem 13A is. Compare the rates of effusion of helium and ethylene oxide at the same temperature and pressure. So we're going to compare how fast does helium move through this hole versus how fast does ethylene oxide move through this hole, because they're going to be different because ethylene oxide is much heavier. So the way I like to solve these problems, I always like to put the compound that has the lower molar mass as this rate part of my equation. So I'm going to say that the rate of helium over the rate of ethylene oxide, which is C2H4O. So because helium has the lower molar mass, that's why I like to put this one on top. So let's just go ahead and make a note of that here. This is just a technique that I usually like to do. So let's see, rate of helium, we like to put the lower molar mass on top. Because you'll see here, then the lower molar mass goes in the bottom of the second portion, and then we get a nice number that's greater than 1. So we're just kind of comparing here this fraction right here. So how many times faster does helium effuse through that hole than ethylene oxide? Let's go ahead and set up the second part of this equation. So we do need to have a square root here. And if I look at this equation, the rate of effusion A, so for us this is helium, divided by the rate of effusion B, is equal to the square root of the molar mass of B. So I have to put the molar mass of ethylene oxide up top here. And the molar mass of ethylene oxide is 44.06 in units or grams per mole. Whereas the rate of, or the molar mass of helium goes on the bottom. So if you look on a periodic table, you'll see that that is 4. Notice how they're opposite of one another here. So let's just go ahead and try to mark this down. Notice helium and helium, they're across from one another. And same thing for the other compounds. So ethylene oxide and its molar mass, they're always opposite of one another. If you solve this correctly, you would find that this whole section right here, you get an answer of 3.32. So 3.32. So what does that mean? Well, that's the rate of helium. I'm just going to write this whole entire thing over again. Over the rate of ethylene oxide. H4O. That's really sloppy, but you get the idea. Now remember, this is technically over 1. Right? So what this is saying is that the rate of helium is 3.32 and the rate of ethylene oxide is 1. So this is saying that helium effuses 3.32 times faster than the ethylene oxide. So helium effuses 3.32 times faster than that ethylene oxide. That's what this is saying right here. In these next two problems, we're going to see that we're solving for what's on the opposite side of this. So let's do B. A sample of hydrogen effuses through a porous container about 9 times faster than an unknown gas. Estimate the molar mass of the unknown gas. Like I said, the first thing I like to do is always identify which has the larger and smaller molar mass. So in this section of my equation, so when we're talking about the rates here, let's just go ahead and start setting this up. So my rate, the lower molar mass would be hydrogen. So my rate of hydrogen over the rate of some unknown. So I'll say the rate of, and we'll just say that the unknown is x here. So rate of x. So that's x. And this equation or this problem is telling us that hydrogen effuses 9 times faster than the unknown gas. So using that and taking a look at what we did in this last problem here, hydrogen is moving 9 times the speed as x. So I'm going to set this numerator up as 9 because whatever the speed is, it's moving 9 times faster than x. So I'm going to set this top portion equal to 9 and the denominator equal to 1, which really is just 9 in general. We want to estimate the molar mass of the unknown gas. So now that we have that settled down, we can set up my square root on this side. And we want to know the molar mass of x. So what I'm going to do is I'm just going to put a capital letter M because that's typically how we denote molar mass. So my molar mass of x over the molar mass of hydrogen. Now hydrogen is diatomic, so its molar mass is 2.02 grams per mole. The way you solve for this, it is algebra, but I'm just going to show you quick. You want to get rid of this square root sign here. So first things first would be to square both sides of that equation. And when you do that, I don't have enough room to continue down, so I'm just going to continue right next door. You get 81, because 9 squared is 81, is equal to the molar mass of x over 2.02. And when you solve for that, so it's just 81 times that 2.02, you get a final answer of 164 grams per mole. Now, I don't think my sig figs are pretty, no, I should have 1 sig fig, but that's a huge round. So it's about 9 times faster. So technically, if we were being really strict with sig figs, which I guess I usually am, the real answer should be about 200. About 200 grams per mole. But either one of these for this problem is just fine. So you can also figure out the molar mass of something knowing, well, if this effuses this many times faster than that, you could find the other side of the equation. Now, sometimes you might be given an actual velocity of that. So that's where this rate section is even more different. We can figure out what that whole number is in this case. So we could say, okay, helium effuses 3 times faster. We can also use that to find the molar mass, but sometimes you might be given exact velocities. So if an atom of neon gas travels at an average speed of 400 meters per second at a given temperature, estimate the average speed of a molecule of butane at the same temperature. Let's put the lower molar mass on top here. So we have neon versus butane. Neon is going to be much lighter. So I'm going to put rate of neon I think with these personally, it always helps to write stuff out. So write this out. Try to get your equation done. Take a second. Think about what you're doing. Don't just try to plug numbers in haphazardly. Like for me, if I don't write this out, then I'm like already like I get stressed out. So write that first part out. I feel like that helps. And we do have the actual rate of neon right here. So that's this 400 meters per second. So that's the rate of neon right there. So let's plug that in on top. 400. Do actually have 3 significant figures there, which is nice. And I'm trying to find the average speed of butane. So I'm just going to keep the rate of butane down below. That's what I'm trying to find. Is what actually is that quantitative speed through that pinhole. And then let's set up our square root and fill in molar masses. So molar mass of butane goes on top here, and your molar mass for that is 58.14 grams per mole. And your molar mass for neon is 20.18. Now remember, when you solve this, well, this one you could solve. You don't have to. You can if you want square both sides. I would probably just solve for this whole section first and then go ahead and do that. Either way, you try to solve that on your own. I'm just going to tell you what the answer is. So you should find that the rate of butane, now if you were to estimate, it should be lower, right? Because it's much heavier. And it is, in fact, it's 236. So you can calculate an actual velocity for butane from that other information. And that's the whole idea behind Graham's law of effusion. I like to talk about it here, although you might not have to calculate this in AP chemistry. I do want you to calculate it just a little bit for me. I don't really harp on this too much. But in AP chemistry, you do need to know that gases with a lower molar mass can effuse or diffuse, which is the spontaneous mixing, much faster than compounds or elements with a much higher molar mass. We're going to do some more practice with this in class because there's not too many problems with this, and there's so many different ways that these problems can be given to you. So they do just take quite a bit of practice, and like we're going to do some of that in class. As always, if you have any questions, let me know. Make sure you stop by and see me. Otherwise, I will see you in the next video. Bye.